In this video, I will be introducing bracket notations. The bracket notations are widely used in quantum computing. These notations are also known as Dirac notation because it was introduced by physicist Paul Dirac. It is a compact and convenient way of representing quantum states. In the previous video on what is meant by quantum bits, we have seen that the quantum states are nothing but a combination of quantum bits. It One of the reason behind its widespread use in quantum computing is that it simplifies complex mathematics of quantum theory. And you can remember this bracket notation consists of two different notations basically. One notation is called as bra notation, which is less than sign followed by one vertical bar. And the second notation is typically called as Ket notation, which is a vertical bar followed by greater than sign. And in between the less than and vertical bar of bra notation, we write a quantum state. Also, in a Ket notation, which is a combination of a vertical bar and greater than sign, we write a quantum state. You can remember this bracket notation in a simple way by writing bracket and enclose it in two angular less than and greater than sign and put a vertical bar in between these two words. So the first combination is called as the bra notation and second combination is called as the Ket notation. So hence the bracket notation is a combination of two different notation. One is called bra notation and second notation is the Ket notation. So this is the combination of less than vertical bar sign and greater than vertical bar sign and greater than. So this bracket notation takes different form and their purpose is also the different. The first for there it takes the six different form in the Ket notation, which is a very simple Ket notation. Vertical bar followed by greater than sign. This Ket notation is typically used to represent a column vector, whereas the bra notation is used to represent a row vector. A combination of two Ket notation, we call it as the Ket notation, is used to perform the tensor product of a column vector, Ket notation. And the bra notation, which is a combination of two bras, is used to represent the tensor product of row vector. Ket bra notation, which is a combination of Ket followed by bra, is used to represent a matrix of m by n dimension. And bracket notation, which is a combination of first bra notation followed by Ket notation, is used to denote the inner product of vectors. So let us first discuss the Ket notation. As we have seen in the previous slide, The Ket notation is used to represent a quantum state. A quantum state may be a zero. In the previous video, I have told you, I have we have seen that quantum state zero is represented like this in this notation, and we read it as the Ket zero. In the same way, another quantum state is the quantum bit 1. Quantum bit 1, quantum bit 1 is denoted like this, which, and we will read it as Ket 1 because this is a Ket notation. We as the block sphere is used to visualize a quantum state, but the visualization does not help us to perform the computation. We need to perform the computation, we need another way of representing the quantum state. And here we are representing the quantum state through a column vector or a Ket notation. This quantum state, which we call it as the qubit zero, and now we are reading it as the Ket zero, is nothing but a column vector, is nothing but a column vector of size 2. Means that there are two rows and one columns are there, single column. A column vector has only one single column. And here in this column, there are two, in this column vector, there are two rows are there. And this row is called as the zeroth row. And this row is called as the one first row. And in order to denote the quantum state 0, we will write 1 at the 0th position and 0 at the 1st position. Similarly, the quantum bit 1 represents the quantum state 1, and we will read at it as the Ket 1, Ket 1. And this Ket 1 can be represented by a column vector of size 2 having two rows. But here the 1 is present at the first position if we number the rows from 0. So try to understand the difference between the Ket 0 and the Ket 1. The Ket 0 is a quantum state 0, and the 1 is present at the 0th position if we represent it through a column vector. And when we represent a quantum state 1, it will we are going to read it as Ket 1, and we are going to represent it as a column vector where 1 is written at first position. It is not necessary that a quantum state is always a 0 and 1. This is another quantum state. We are going to read it as Ket 1 1, and its column vector representation will have the 1 at the third position if we count the number of rows from 0. And if we denote this through binary digits, classical using classical bit, this is become 0 0 0 1, then 0 2, then 0 3, or sorry, uh, so this is 1 0, and this is 1 1. So 1 will have the at 1 1 position or the third position for Ket 1. So similarly, if the this state, another example, in this example, it we will read it as Ket 101 is nothing, and we need to represent this state. We need 7 rows now. So if we count it from 0 0, it will be 0 0. The first row will have 0, and it is the 0 0 1. The second row will be 0 1 0 position. Then third is 0 1 1 position. 0 will have 0. Then fourth will have again 0. The fifth we will have value 1, and 1 0 1 1 1 0, and 0 will be present at 1 1 1 position. Suppose that if we want to represent n bit of information, n bit of information, then we need a column vector of 2 to the power of n. So here 2 to the power of n with equal to 2 to the power of 2 equal to 4, we can represent 2 bit of information. If we are using 3, then 2 to the power of 3 will have 8, and we can represent a 3 bit of information. Similarly, to represent a 4 bit of information, we need a column vector of size 16. Now, sometimes we have given a column vector and we want to represent it through a Ket notation. Let us take one example. For this is a column vector, and 7 is present at the first column vector of size 2. Here number of rows are 2, and 7 is present at the first position, and 3 plus 5i is present at the second position, or 7 is present at the 0th position, and 3 plus 5i is present at the first position if we count the number of rows from 0. Now, in order to represent this column vector through a Ket notation, we write, because uh, 7 is present at the 0th position, 7 will become the coefficient of Ket 0, and 3 plus 5i is present at the 1 position. 3 plus 5i will become the coefficient, and Ket 1 becomes the state. Here we are using two different types of quantum state, that is 0 Ket 0 and Ket 1. So the basis used is Ket 0 and Ket 1. Now let us take a second example. In the second example, we will have a column vector of size n equal to 4. And here n equal to 4, we need a two different bits. So the 7 is present at the 0 position, 0 is present at 0 1 position, I plus 3 is present at 1 0 position, and 0 is present at 1 1 position. In order to convert this column vector into the Ket notation, go from the first row to the last row and skip the rows at which value 0 is present. Now here the non-zero is the 7, and this is present at the 0th position, so make it 7 will become the coefficient of 0 0 state. And I plus 3 is next non-zero number. So I plus 3 becomes the coefficient of quantum state 1 0. Here we are using two different quantum bits. So the basis used is 0 0 0 1 1 0 and 1 1. So in this way, you can convert a column vector into Ket notation, and given Ket notation, you can write a column vector for that. Now the second type of notation is the bra notation. If the Ket notations are used to represent the column vector, the bra notation is used to represent the row vector. A row vector is a vector or having is a matrix with only one row. So, and the bra notation consists of two different symbols. One is less than sign followed by one vertical bar. Here, this is the it will read as the bra zero. Now, bra zero's equivalent represent row representation is a vector having 1 at the zeroth position and 0 will be at the first position. Similarly, a bra1 consists of a row vector having 1 at the first position and 0 at the zeroth position. The the Ket and the bra notations are interconvertible. Interconvertible means that you can transform one notation into the another notation. And in order to convert one notation into the another notation from Ket to bra or bra to Ket, you need to take the perform the plus operation, which is nothing but the conjugate transform. Conjugate transpose. Here the conjugate is taken for a complex number. If the x plus iy is a complex number, its conjugate is x minus iy, and transpose of a vector means that in you will we are going to convert rows into column and column into rows. So that is the matrix operation. Transpose is a matrix operation and conjugate is a complex number operation. So this plus symbol is a combination of two different operations, one from the complex number domain and another is from the matrix. Here we are taking one example of converting a bra notation into the Ket notation. So here bra psi consists of 3 minus 5y times bra 0 and plus 7 times bra 1. Its equivalent row vector representation consists of 3 minus 5y at the 0th position and 7 at the 1st position. Now, if we want to represent it in the Ket notation, we need to take the complex conjugate transpose of this row vector. Here the 3 minus 5y becomes the 3 plus 5y and row becomes the column. The 3 minus 5y and 7 row becomes the column 3 plus 5y and the 7. Non-complex numbers are kept as it is. And this vector is represented in the Ket notation like this. 3 plus 5y Ket 0 plus 7 times Ket 1. So in this way, you can convert a Ket notation into bra notation and bra notation into the Ket notation. Now, sometimes what happens that you have given a row vector and you need to represent it using bra notation. Now, since let us take one example here, a row vector consisting of four different elements. Since there are four elements, we need 2 bit of information. To represent the four different type of information, you need 2 bits. So the 3 is present at the zeroth position. So make the 3 as the coefficient of the bra 0 and skip the zero value, zero, the rows at which the zero value is present. So we are going to skip this, and I is present at the 1/0th position and 7 is present at the 1/1 position. So make the I as the coefficient of bra 10 and 7 is the coefficient of bra 11. Here we are using four different types of states. So the basis used here is 0001, 10 and 11. Third type of bracket notation is a combination of Ket notation. Ket notation. Here we are going to use two combinations of two Kets, and this is typically used to represent a tensor product of column vectors. Since Ket notation is used to represent the column vectors, here we are using the this combination of Ket notation is used to represent a tensor product. Here I am going to explain what does it mean by tensor product. Tensor product is a operation that is usually performed on matrices. Here two different matrices are given, A and B. So these are the first matrix is of the size 2 by 2 and the second matrix is of the size 3 by 2 where three columns are present, sorry, 2 by 3, uh, uh, two columns are present and two rows are present and three columns are present. The size is 2 by 3. A tensor product multiplies the elements of the first matrix to all the elements from the second matrix. Here, the first one is the element from the first matrix, and a multiplication of the second matrix is taken by multiplying with the one with it. In the second position, the second is the element present at the second column and the first row of the first matrix, and 0 is present at the second row and the first matrix, second row and the first column. We are multiplying it with the second matrix. Similarly, 2 dot b means 2 is present at the second row and the second column, and we are multiplying the second matrix with 2. If we perform this multiplication, we will get a tensor product matrix. So focus on this matrix, this submatrix of the tensor product, and this we will get by multiplying matrix B with 1. So if we multiply this matrix with 1, we will get the same matrix 1, 2, 3 and 0, 4, 7. Now focus on this subgroup of matrix, and here we are multiplying second matrix with 0. If we multiply 0 with the second matrix, we get all elements 0. So focus on this subgroup And here we are multiplying 0, taking the multiplication of second matrix with 0, and we will get this matrix. And if we focus on this subgroup of matrix, here we are multiplying second matrix with the save 2, because 2 is present at the second row and second. So we will get 2, 4, 6, 0, 8, 14. So this is the 1 times B. This matrix is the 0 times B, and this subgroup matrix is 0 times B, and this group is 2 times B. The matrix B is this B matrix. So this, in this way you can calculate the tensor product. And the Ket-ket notation is used to represent a tensor product of column vector. Let us take the example through Ket notations now. Here first psi is the state, or psi is a function where I times ket 0 plus 7 times ket 1. The second is the phi function with ket 0 0 and ket 3 times ket 1 0 and 7 times ket 1. So in order to calculate the tensor product, first multiply I 1 0 with second, and you are going to get I 0 0 0. Now take multiply this I 0 with the second element of the phi function. So if we multiply this, you will get 3 times I and 0 1 0 ket. So here I have written 3I 0 1 0. If we multiply I with the third element, we will get 7I, and 0 is present at the, from, we are taking from the 0 first function, and 1 1 from the second function. So 7 times I 0 1. So I will get 7 times I 0 1. Now let us multiply, take the second element 7 and take its multiplication with the each and every element of the second function. So 7 times 100, because this is 7 and 1 from first function, 00 from the second function. Now if we multiply 7 7 ket 1 with the second element, I will get 21. 7 multiplied by 3, 21, plus ket 1 from the first and 1 0 from the second. So 21 times 110. Similarly, if I take multiply 7 with this 7 ket, 7 times ket 1 with 7 times ket 1 1, I will get 49, and first one from the first function and second one from the second. So I will write 49 times ket 1 1. So this is the vector representation of first function ket psi, where I is present, coefficient of I is present at the 0th position and 7 is present at the 1st position. Similarly, the vector representation of phi is, the phi function consists of 3 elements. One is the coefficient of 0 0. There is no corresponding term 0 1, so 0 is written. So 3 is the coefficient of 1 0. So the 3 is present at the 1 0 position. And 7 is the coefficient of 1 1. So that's why 7 is present at the 1 1. And if we take the tensor product of these two column vectors, I will write I times 5 and 7 times 5. And if I multiply I with the second vector, I will get I 0, 3I and 7I. So this vector is I times 5. And if I multiply 7 with the second column vector, I will get these elements 7, 0, 21, and 49. So this is nothing but the 7 times 5. So this is about three different types of Ket notations. Thank you.